So we looked at one of the most expensive parts of the air conditioning system, which was the compressor so far. And now we're going to switch to perhaps a not so expensive part, but which is equally critical to the performance of an air conditioner. And this is expansion device. So just like we have a pressure increase across an active compressor, we have a pressure drop across the expansion valve. Or rather the expansion device, and then we will have a separate nomenclature for expansion valves as we go to the next slide. So any restriction can be used as an expansion device. We are trying to prevent a refrigerant flowing freely. So any restriction that we create is an expansion device. The function of the expansion device is, number one, to make refrigerant flow at a certain rate to the evaporator. So it's like a control device. The rate of heat rejection in the evaporator has to be matched by a corresponding mass flow rate of the refrigerant. So that is one function which is met by the compressor together with the expansion valve. There is another function which is the pressure drop that we need. We have liquid refrigerant, and we want something to which we can reject the heat from the air conditioned space or from the refrigerated space. So we need to get to a temperature lower than the temperature of the body from where we want to remove heat, and that is accomplished by dropping the pressure, which happens across the expansion device. Now there are several types of expansion devices. The first category is fixed type of expansion devices, which means there is no variation in the restriction that they offer. So one of the easiest ways to look at an expansion device which is fixed is a capillary. You have a certain length, you have a certain diameter, and the restriction that it will offer is then constant. The flow rate of the refrigerant will depend, of course, on what is the pressure at the inlet, what is the pressure at the exit in some cases, but it will depend purely as a physical property of a fixed orifice and a fixed length. We could also have something equivalent to a manually throttled expansion valve, like a tap. You can control the flow rate. So manually you could control the flow rate of refrigerant with a manual throttling device or manual expansion valve. And then we have variable expansion devices, which are of two major types: automatic expansion valve and thermostatic expansion valve. Within the thermostatic expansion valve we have another two categories, which is internal equalization of pressure and external equalization of pressure. That's easy, clear? Now capillary, I don't have a picture, but it is very easy for you to imagine. Just a thin tube with a diameter which is some 1 millimeter, 2 millimeter length, somewhere from 35 inches to 55 inches, used in most low cost refrigeration systems. So in your domestic refrigerator there is a capillary. In your normal air conditioner split system of 1.5 ton that you use in your homes, there would be a capillary. It is the lowest cost expansion device and still pretty effective. When you are targeting a fixed point performance, it is possible to optimize the capillary dimensions such that you are able to match the pressure drop needed for those operating conditions. It is also possible to take care of some of the adverse conditions by doing proper sizing. Then we have the hand operated expansion valve that you see in this picture, and if you relate to the cross section of a tap, it is exactly that. You have a stem, so this is the stem. This cap is there because we don't want refrigerant leaking. So once we've adjusted it, we would put this cap so that no refrigerant can leak between the seal of the shaft and the outer body. The pressure drop really happens between this point and the body. So we can move manually the shaft up or down and thereby alter the opening that is available. Then we have an automatic expansion valve. In an automatic expansion valve, the intention is to keep the evaporator pressure constant. So how do you accomplish that? So we have fluid coming from the condenser. It is subcooled liquid, it gets into this zone, and then we want it to pass through the throttling device. The difference between the manual throttling device that we saw in the previous slide, where it is fixed once you have adjusted the stem, and this one is that there is an active element. There is a diaphragm. So, this is a disc, typically a stainless steel disc which is flexible like a bellow. It would move up and down based on the spring pressure which is coming on from the top and the pressure of refrigerant coming from the evaporator. So, let us take a scenario when the pressure goes low. So, the spring force is constant. So, if the spring force is constant and the pressure from the evaporator goes low, what is likely to happen is that there will be movement downward. So, the conical section that you see here, this will have a larger opening, so a wider flow happening. So, when the pressure goes lower, there is more refrigerant flowing in, so the pressure will rise. And similarly, if the pressure were to be too high, then this would push the diaphragm upwards, closing it, so less refrigerant is flowing in, and therefore the pressure will reduce. So, this is an actively adjusting device which is throttling, but with an intent to keep the pressure in the evaporator constant, and you would need such a device when you want a constant evaporating temperature, because at saturation these two are related. So, if you are targeting a constant evaporating temperature, you would do this. This is not the most commonly used expansion device. So, now what we are going to get to next is a thermostatic expansion valve. So, here on the left you can see a cross section of a particular type of expansion valve where there is a straight connection. So, refrigerant comes from the left and leaves from the right. It is a straight through, and on the right is a picture of an angle connector expansion valve where the refrigerant comes in from the bottom and leaves it horizontally. There are some parts of this expansion valve which we can use the figure to. So, there is first of all the membrane housing. So, this diaphragm that moves continuously up and down in the automatic expansion valve, there is a similar component in the thermostatic expansion valve also. So, over here, and the body this is housing it is the membrane housing. So, in many expansion valve designs it is possible to remove this and use another one depending on what refrigerant you are using, and there are other manufacturers who would combine this, weld it for reasons of preventing refrigerant leak, and that is also an accepted design. Then what do we have next is an interchangeable adapter. So, for reasons of reducing the number of parts and having one body for multiple capacity applications, it is possible to change the orifice where the expansion happens, and then the flow rate properties of the refrigerant will change. So, this is another part which is an intricate part of the expansion valve. Then we have a spindle which is part number 4, or before that, 3 is the housing. So, the body of the valve is part number 3. Part number 4 is an adjustment for static superheat. So, the spring force can be altered when we are optimizing the system. So, you move it counterclockwise and counterclockwise, we will be either compressing the spring or relaxing it, and with that the spring force on the diaphragm will change. And then we have a refrigerant filled bulb. So, this is a key departure from the automatic expansion valve. In the automatic expansion valve, the variable we were looking at was pressure. So, we wanted constant pressure in the evaporator so that we have a constant evaporating temperature against which we can have heat exchange. Here we are replacing that with a bulb. So, from a pressure, from monitoring pressure, we are looking at monitoring temperature using a bulb which is filled with refrigerant, and usually the refrigerant is not the same as what is used in the system because of reasons that we are going to get into later. But we want a temperature signal to be modulating the diaphragm so that we can control the superheat at the outlet of the evaporator or inlet of the compressor. Now, here we can see an expansion device in the refrigeration cycle. This is in a very simple refrigeration cycle where there is no distributor. Now for those of you who are wondering about what a distributor is, there is another element which comes between the expansion valve and the evaporator for large systems. So if we have a 5 ton or a 7.5 ton evaporator like a package unit, an air conditioner, we would have multiple circuits feeding the evaporator. So the refrigerant enters the distributor as a tube, like as liquid in a typical half-inch diameter tube, and then there are smaller tubes, maybe 1/4 of an inch or 3/16 of an inch, that leave the distributor feeding individual circuits in the evaporator. And you don't have to remember all of this right now, because when we look at heat exchanger design, we will look at circuiting and optimizing it. But I want to mention that this is a simplistic representation. Most systems where an expansion valve is used, we would have a distributor which would distribute refrigerant to different circuits in the evaporator. And then here you can see the bulb. It is going across the evaporator and it is on the suction line, leaving the evaporator, connecting to the compressor. This is where we are going to sense temperature. So how do we convert temperature into a modulating signal? Is we put this bulb, which is filled with refrigerant, in contact with the pipe. So there is good thermal contact. Out of conduction, whatever is the temperature of refrigerant in the suction tube, it would be a good assumption that that will be the temperature of the fluid inside this bulb. And varying temperature would lead to varying pressures in the entire system, which begins from the bulb and goes right up to the top of the diaphragm here. Right. Now here what's going to happen is we have an evaporator. So we have the evaporator, the pressure of refrigerant in the evaporator, which is acting on the lower part of the diaphragm. We represent that by PE, P evaporator. Right. So that pressure and the pressure coming from the bulb, PB. For those of you who are not able to read, what is written here is PB, the pressure inside the bulb. And then we have a force, a spring force, which is translated into a pressure term, PS, which is dependent on where we have adjusted it, or if we have not adjusted it, then an expansion valve will be shipped with a fixed setting. So based on the bulb pressure, spring pressure and evaporator pressure, we will define the degree of opening of this orifice. And for that reason, this is a continuously adjusting expansion valve, and it is a thermostatic expansion valve, not an automatic expansion valve, because we are sensing temperature and then converting it into a pressure signal. So this is one of the most commonly used expansion devices for larger systems where the compressor size increases. We are really concerned about compressor safety. We don't want any refrigerant getting into the compressor suction, and once we put this in, we are sure that it will continuously keep varying. No matter what happens to the evaporator load or other system conditions, we will have a reliable operation. Then we have another expansion valve category, which is thermostatic expansion valve with external pressure equalization. So if you see this simple system, we have connected the evaporator pressure directly, and we don't seem to recognize any pressure drop in the evaporator. We kind of assumed that the pressure here and the pressure here is almost the same, which will be true for some systems which are simple systems, and therefore using a internally equalized expansion valve is fine. But when there is a large pressure drop and there are evaporators which have a liquid distributor, which I mentioned before, then the pressure drop is significant for us to move to an externally equalized expansion valve. So what happens in an externally equalized thermostatic expansion valve is, instead of using this pressure from the evaporator act on the lower surface of the diaphragm, we put in another tube. So this is a copper tube which would connect the point at which we place the thermostatic expansion valve bulb to the lower end of the diaphragm. So here what has changed is the bulb pressure remains the same, the spring pressure remains the same, and we have pressure at the thermostatic expansion valve bulb location. So, it is more accurately representing saturation conditions at the evaporator outlet, or more correctly said, at the point at which we are sensing the bulb. So, this is a little more detail on the construction, the cross section of the internally pressure equalized expansion valve. As you can see, it is simple. The hole for equalization is right inside, so we do not really need to worry about any tubes. And in case of an external pressure equalization, there is a port. So, in addition to the liquid line which enters from the bottom and the suction line leaving horizontally, there would be another tube, a copper tube, which will connect the port. So, we will need some adapters. This is a threaded connection, or we could also have a soldered connection, and those are other variants of expansion valves when we are designing a system as to how we want to connect it. When you are looking at airtight systems, we are looking at reliable systems where there is no need for replacement, then we would look for soldered connections for all these parts here. When we feel there would be likely a need for making changes, then we would look at threaded connectors. What are the advantages of internal pressure equalization is that there is no additional piping needed. It is a simpler system. Pressure after the valve is used at evaporative pressure under the diaphragm, which we have discussed, and the pressure drop is not taken into consideration, which means it is negligible, or we are adjusting it using the spring force if it is constant. This we would do when using distributors. So, we have more or less covered this, and the whole idea here is that if the pressure drop in the evaporator is more than 1 degree Kelvin, so we are saying pressure drop and 1 degree Kelvin means you are looking at saturation conditions. So, then we would use a externally equalized expansion valve. Superheat, we have discussed the theory, but if we were to look at measuring it in a system, then this is what we would do. Possible to read, right? Not easy. So, superheat is measured at the evaporator outlet at the same point where the bulb is located on the suction line. So, if we are looking at verifying the performance of a thermostatic expansion valve, we would do this. We would tap the suction line, which means we would intrude into the system, we would take a pressure reading and we would take a temperature reading. So, if these were the two readings taken, then we would convert the pressure to its corresponding saturation state, and then the difference between the real temperature and the corresponding saturation temperature will give us the superheat. And as we discussed before, the key purpose of maintaining a superheat is to prevent liquid refrigerant getting into the compressor. Now, in some cases where we do not want to puncture the system and we want to still get a reasonable estimate of the superheat, we could do this. We could take the temperature somewhere in the middle of the evaporator where there is a two-phase phenomena happening, which means evaporation is happening. So, we can directly take that, and by doing so we are assuming the pressure drop from that point to the suction is not significant. So, we would take this temperature and we would take this temperature, and the difference between the two would give us a fairly good idea of what the superheat is. This is an alternate way. Now, where can we run into trouble? If the flow rate, now this is a distributor here. So, this is feeding one circuit, the refrigerant flows and then gets to the header, and then there is another circuit, again refrigerant comes in and goes to the header. If the refrigerant flow in both these circuits was not equal and we end up taking temperature here, then we could be running an assumption which is not really valid. So, we could get to a superheat value here, but in reality there could be liquid flowing to the compressor because the other circuit is feeding more refrigerant and we have not factored that part. So, the most accurate way to determine superheat would be this, where we have taken the pressure and temperature at the point of interest. Then again we looked at subcooling theoretically. Now, if you are looking at a system where we want to measure the subcooling, we would do something very similar. We would take pressures and temperatures, and the extent to which the temperature at the point we measure the temperature at the condenser outlet is below the saturation temperature, that is the subcooling. We would do these measurements during system design because we want to guarantee liquid going to the expansion device is in liquid state, subcooled state, and that is for reasons of performance. Then something someone asked a question before about vapor bubbles in the refrigerant reduce the capacity and thereby reduce liquid supply to the evaporator and therefore the capacity of the system. So that is the reason we are attempting to keep it subcooled. And typical numbers 2 to 5 degrees Kelvin. If you are looking at highly efficient systems, then we could take this to 12 degrees, even 15 degrees, and that depends on the appetite for cost and what efficiency numbers we are targeting. The other part about subcooling which we need to be careful about is we have been assuming pure substances. So, pure substances means there is no glide effect. When we look at a certain saturation condition, then there is a direct correlation between temperature pressure. But in refrigerants which are mixtures of two substances, there is a glide, and that glide leads to some errors. So, we just need to be aware of that. Then I mentioned about the substance that is in the bulb being different from the refrigerant itself. So, there are different classifications of charges inside a thermostatic expansion valve. So, there is a universal charge, there is an MOP charge, and then there is an MOP charge with ballast, which is for certain brands it compensates for expansion. And then there is an anti-Hunt charge, which is meant for systems where there is high instability. So, the response time is adjusted in a way that the valve is not continually adjusting to varying load conditions. Now, most refrigerant, most of the expansion valves would have in the bulb a combination of at least 2 refrigerants and nitrogen, and the refrigerants not being the same as the system refrigerant. Now, we look at the behavior of the expansion valve in response to evaporator temperature. So, low evaporating temperature means small pressure changes, less valve opening, and a small reduction in mass flow, whereas at high evaporating temperatures there is a high pressure change and there is more valve opening, which means there is a increase in the mass flow rate. So, if you look at the change, a similar change for 5 degrees change in temperature, there is a pressure difference of 1 bar required at high pressures, whereas at low pressures it is just 0.5 bar. So, this is the characteristic curve which is relating the pressure in the evaporator to the temperature for a typical expansion valve, how it is constraining the refrigerant flow. Now, some of this is stuff which you need to look at when you are looking at advanced design optimization techniques. So, it is there for you to know that there is a valve capacity which varies with evaporator temperature. The valve capacity will not be the same at 2 different evaporating temperatures. The same valve will allow for different performance curves. Then we look at cross charge. So, an expansion valve has a substance in the bulb which is different, and what it really means is that the pressure temperature curve can be made flatter, so that it is more responsive to changes in suction pressure, and it reduces hunting of the system. So, one way to relate to hunting is when you looked at this feedback going from the evaporator outlet to the expansion valve, the diaphragm is moving. If that diaphragm movement was too often, it would become a system which would adjust too fast. So, we have choking one stage and then we have full opening and then again choking. So, there will be a variation in pressures and temperatures, and that is what is called hunting, which is undesirable in a system because it prevents steady state operation. So, your cooling is not constant, your components are unduly stressed because of these variations in pressure. Now, the universal charge expansion valves are used in systems where there is no pressure limitation requirement. Now, pressure limitation requirement is, let us say we talk about a refrigeration system, we are maintaining a temperature of minus 25. The evaporating temperature is minus 30, and such a system, when it is switched off, what is likely to happen? the refrigerant would come closer to the temperatures in the ambient, and when we start the compressor there could be a possibility of overload. So, there is a need to control the refrigerant flow using expansion valve in a manner that we do not overload the compressor in systems designed for low temp applications. Not all systems have those limitations. So, if you talk about a package system which is used, or a chiller system for comfort, they are not normally encountering that limitation, and for those applications, simpler applications, we use a universal charge. The amount of charge that remains in the bulb is irrespective of whether the element is in colder or warmer state. See, if you look at an externally equalized thermostatic expansion valve, there is fluid inside this bulb and there is a diaphragm. If the temperature here is higher, there could be migration of the refrigerant from the bulb to the diaphragm, and in certain conditions, if all the fluid were to move out from the bulb to the space above the diaphragm, then there would be nothing to sense what is happening to the temperature at the suction line. So, there are valves where it is specified that the bulb has to be in a place which is cooler than the diaphragm body. So, when designing system, we would keep the expansion valve body location in a warm area, which means the refrigerant is always in the bulb. The substance that is used for sensing temperature is always in the bulb. Now, in universal charge, the charge quantity is so high that no matter what happens, there will be always a certain amount of liquid in the bulb, and therefore it will continue to sense, and therefore it is relatively robust in terms of application. We are not constraining the engineer to ensure that the temperature is lower or higher. And then we have the MOP charge. So, the MOP stands for max operating pressure. And what we do in a max operating pressure situation is that we will cause the refrigerant inside, or the substance, more accurate term is the substance inside the bulb, to vaporize completely at a certain temperature, so that it does not open the valve any further. So, that is to limit the suction pressure at which the system will operate. So, now these will be used typically on factory made units where suction pressure limitation on starting is required, for example, in transport sector. So, let us say there is a refrigerated truck and it has been kept empty for a few days, and then suddenly it is loaded with fish which has to be transported at low temp. So, the expansion valve will tend to feed maximum refrigerant in the beginning, and that is not what the compressor has been designed for. It has been designed to maintain the system at a certain point. So, take care of that transition when the compressor is started. We will have an MOP limit the quantity of refrigerant flowing in there. So, here if there is a universal charge, then as the temperature rises, the flow will increase, whereas a valve with MOP at a predefined design point, it will just flatten out, and the bulb pressure then does not increase, which means there is no further opening of the thermostatic expansion valve. We have the highest risk of charge migration in an MOP valve, because we have limited the substance in a way that all of it will evaporate at a certain condition, and there will be nothing left to further increase the pressure in response to increased suction line temperature. So, what we are saying is that we will allow the superheat to rise, but we will not feed additional refrigerant. Since we have reduced that quantity, there is a risk of migration which is highest in case of an MOP charge inside that sensing bulb. And to address that, then comes another design innovation, you can say, where we put in a ballast in which the fluid is not really free to migrate. So, what an MOP charge with a ballast does is it has a damping effect on expansion valve regulation. And then one of the companies that I worked for, it uses this as a standard MOP charge. The valve opens slowly as bulb temperature rises, closes quickly as bulb temperatures drop. The bulb must always on average be colder than the thermostatic element, and the refrigerant charge will move to the valve, and on an average it will form better. Now, these valves with MOP ballast would become useful in certain unique heat exchangers which are called multi-channel heat exchangers, and then braze plate heat exchangers. In braze plate heat exchangers, we are having heat transfer occur between two parallel streams of water and refrigerant, and there is a high degree of responsiveness required because the refrigerant volumes are really small, the system is small and compact, and if we don't have the adjustment quickly, then we will have big challenges to reliable operation of the compressor. So, if you look at a summary of the different type of charges that are available in an expansion valve, then this would be, universal charge would be for addressing a wide temperature range where there is no need to constrain the operating pressure. MOP is where suction pressure during normal operation, but during the startup of normal system, the compressor must be strong enough to empty the compressor. So, basically what I said before is a much more accurate description, that if you want to limit the suction pressure during startup, then MOP would be the best choice. And anti-hunt valves would have a charge which would address dynamic scenarios much better. So, it would compensate any kind of hunting characteristics of the system. So, it is basically a delayed response. So, you have tuned the response in a way that you do not allow hunting to happen. Then there is another aspect of expansion valves which we must be aware of, but what happens is when a system is stopped in an expansion valve, we could keep the high pressure and the low pressure zones airtight from each other, or like pressure tight from each other, which means we stop the system. If the discharge pressure was 300 psi, it stays there, suction was 77, it stays there until the compressor is required to restart. Now, a number of compressors have limitations on torque when they start, and they would not be able to start if the pressures are not equalized across the suction and discharge. So, the need arose to consider some means of causing a small leak of the refrigerant, so that in the off cycle both sides, the suction and the discharge, come to the common pressure, and then the starting torque requirement is reduced. So, that is accomplished by providing an expansion valve which has a bleed. And another thing to remember is in capillary systems there is naturally bleed happening, because that there is no adjustment, there is nothing, whatever we designed for is available for pressures to equalize, and all residential systems, refrigerators, they equalize through the capillary. It is only in expansion valves where we are controlling the orifice opening that there is a need to look at this aspect. So, this is what devices with a bleed will look like. So, instead of allowing for a pressure tight seal, you provide a small groove on the edges here. So, these two are the bleed ports. So, instead of allowing a seal which is pressure tight, there is a small groove provided which will allow for refrigerant to leak, and typical off cycles for a compressor could be 5 minutes, 3 to 5 minutes, and the cycle times could be very different if the load conditions are different. So, you could have off times even longer. So, when you are designing a system, if in 3 minutes you are able to equalize, it is perfect. Now, what happens with the bleed port valve is, in addition to the flow that happens through the regular opening, there is a small amount of refrigerant flow that will happen through the bleed port. So, we have to compensate for that in our estimates calculations, and normally the designer does not need to worry about it because it is already factored in the selection parameters that we will use for expansion valves. Then in terms of design parameters, the size of the bleed can be 10% or 15% of the total refrigerant flow that we have sized the expansion valve for. And there is no thumb rule except doing a test to find out what percentage bleed would be sufficient. So, this is a part of the rigor of proving system performance during reliability testing, that we have addressed this comfortably and there is no issue. Then we come to a slightly more interesting part of an expansion valve, which is what is the minimum stable superheat, and there is some theory or background to what is minimum stable superheat. So, what you see in this slide is refrigerant which is a mixture of vapor and liquid, which is progressively moving into different types of flow, which could be slug, mist, etc., till in the end there is superheated vapor. Now, valve capacity is a function of superheat. So, the higher the superheat, the more will be the valve capacity, because we are adjusting it in response to superheat, right. Now, in a valve there is a certain spring force, so there is a static superheat. So, static superheat you can remember as something which is directly correlated to the spring force. We have adjusted a certain setting and that is what we have. And then there is a part in which there is an operating superheat, which is superheat required to move the valve pin from its closed position to its fully open position. And if we add the two, static superheat and operating superheat, then that is the entire performance area of the valve. And here we come to the minimum stable superheat theory. So, the minimum stable superheat is a function of the load, the evaporator temperature, the airflow, coil design, and a whole lot of evaporator design parameters. The point we need to understand here is we looked at compressor and we find that the expansion valve depends on the compressor in terms of sizing. Similarly, the superheat parameter that we use for the evaporator depends on the evaporator design. So, we have not touched heat exchangers yet, but the kind of airflow in the evaporator will determine what kind of stable superheat we can operate it. And the intention behind having the minimum stable superheat is to keep the discharge gas temperature as low as possible. So, we have superheat which we need to prevent any liquid getting into the compressor, but we do not want excessive superheat, because then we will end up de-superheating in too large area of the condenser, and we will lose out on the effectiveness of the condenser. Are you with me on this? Why do we have a discussion around minimum stable superheat? It is a parameter that impacts cost. It impacts our ability to optimize the heat exchanger and the system together. And then every evaporator will have its own unique minimum stable superheat because of the design criteria. How many circuits it has, which circuit is loaded, how the airflow pattern is there, and all that. So, here we are now crossing into the zone that when we look at one component, we are also having to look at an overlap with parameters of another component. So, if we keep the superheat too small, what happens is that we looked at that example of two circuits. So, one circuit is feeding a small quantity of liquid refrigerant and another circuit is feeding vapor, and the two are getting mixed up. So, the expansion valve opens in response to droplets coming in from one circuit, and then it responds to vapor, because there will be a continuous movement up and down of the diaphragm and therefore throttling, and then we will want to adjust it higher. So, as we adjust it for the circuit which is least loaded, we will starve refrigerant in a good part of the other circuit. So, that is why this mention of fingerprinting of every evaporator. So, when we start optimizing, we want every circuit in the evaporator to be almost equally loaded, and then we strike a compromise that fine, we could do so much and we can't go beyond this, we cannot be making the perfect evaporator. So, we will tolerate a certain part of the operating superheat to allow for stable operation. And I think all the parameters that are mentioned here I have already discussed with you. So, that kind of pretty much covers this part of. This I am skipping. So, here we come to a certain summary of what we covered so far. So, we looked at application, we looked at refrigerants, we looked at we have not looked at evaporator capacity maximum and minimum yet, but when we do the expansion valve sizing, we will need to look at that. So, right now we talked about the operating envelope for the compressor. So, implicit in that is the minimum maximum cooling capacity that we are considering, and we will need that when we are selecting the expansion valve. And as you see, more and more we get into parameters for selection. Whatever was needed for the compressor selection is equally relevant for the expansion valve, except that we are dealing with some new terminologies like thermostatic expansion valve with minimum stable superheat. We are looking at some circuiting details and all that, but the core parameters that we derived from the pressure enthalpy diagram remain the same and are equally relevant for both the expansion valve and the compressor. Another simple way to look at expansion valve selection is to use whatever engineering tools are available to define the pressure drop that happens across the expansion valve, because it is an orifice and then we look at what will be the minimum pressure drop, and at that minimum pressure drop what is the maximum flow rate of refrigerant that we need, and then we look at the maximum pressure drop, and at that what are the two minimum and maximum flow rates that we can accept. Once we have done that, then the thermostatic expansion valve will operate pretty effectively because we have addressed the extremes. So all the region in between will work there. So that is one approach to selecting an expansion valve very effectively. Then we have covered subcooling, how to measure it, as well as the theoretical aspect of how it impacts energy efficiency, the net refrigeration effect. Then we have looked at physical requirements. I touched upon it very briefly, like the solder, angle and straight, but those are things that when you begin to build a physical system, you will have the liquid leave the condenser in a particular orientation. You would want to feed it to a distributor in a particular orientation, and then you will make your decision about whether to use a straight through or an angle expansion valve. Most commonly used expansion valves are angle expansion valves because the need to divert refrigerant flow. It is handy to have something which has refrigerant come out from the evaporator horizontally and then go vertically down or vertically up. Sorry, condenser. So from the condenser you come to the distributor and then this whole part happens. So you're normally feeding from the expansion valve to a distributor, and having that angular configuration is useful. And if you look at an example of a frozen food storage with 2 evaporators and 1 compressor and a refrigerant 404A, then we will typically have something like this for selection. We will have the capacity. So if there are 2 evaporators, 2 into 10 kilowatts, evaporating temperature, condensing temperature, subcooling, liquid line, size, and then whether or not MOP is required. So since this is a evaporating temperature application of -30, we will end up making use of an MOP valve. Then if you look at what a typical selection table will look like, and here are the valve numbers. Then we have an orifice number. So the valves with interchangeable orifice, we can put any one of the orifices, and then for a predefined pressure drop there is a flow, the refrigerant capacity that is defined here with a compensation for the subcooling. So if you are looking at pressure drop across the expansion valve, some of the easy steps would be to look at evaporator pressure, condenser pressure, and then what are the pressure drops across line components. So whatever line component you will choose, whether it's a filter dryer, distributor, you will know what is the pressure drop. You can calculate the pressure drop in the pipelines and then come to a number which represents pressure drop across the expansion valve. And then we also address some of the height differences, and if there is any liquid column that is going to need to be adjusted for the calculations, we will do that. So this is more like in a schematic how we can look at delta P. Are you able to follow this? So this is just an example of all that I just said, that you could pick up a particular refrigerant, you would take the condensing temperature, evaporating temperature, subtract, get the difference in pressures, and then also take care of whatever is there in the lines. So with this we are more or less done with the thermostatic expansion valve selection criteria and an overview of how it operates, and I would like to conclude our session today over here. So thank you.